How's it going, ladies and gentlemen? Mr. Donahue here once again. This time we're going to take a look at nuclear fission and fusion. So our objectives will be to explain the process of nuclear fission and fusion and how these nuclear reactions have been utilized as power sources and weapons and the engineering behind them. So vocab, let's start there. Fission is the splitting of heavy nucleus, either spontaneously or due to a collision with the particle, with the release of energy. So you can see an image off to the right here. We have a large nuclei being hit by a neutron here and splitting into smaller nuclei. So splitting is fission. So if you think back to biology, binary fission is when it splits in two and you get two things. So fission means to split. Fusion is the combining of smaller nuclei to make a bigger one with the release of energy. So here you can see we have smaller nuclei coming together and making a bigger one. So it's what happens when things get fused together. So you think of fusion, think of multiple things coming together to make one bigger thing. So again, a closer look at these images, you can see a large nuclei being hit by a small particle, which is causing it to become unstable. And then it splits into two different nuclei. Whereas fusion is the opposite. We start with two nuclei and they come together to make one bigger nuclei, and sometimes like a neutron or some other particle is also given off. So fission, often used in power plants. So whenever you're talking about nuclear power and nuclear energy, we're typically talking about fission reactions. Whereas fusion, the sun is it's a large fusion reactor. It's giving off a bunch of energy. Currently, we haven't figured out a viable way to use fusion power. But wait a minute. How can fission and fusion both release energy? You said fission was splitting of a nuclei, releasing energy, and fusion, you said, was two nuclei coming together to make one big one and releasing energy. All right, so how is that possible? How can they both give off energy if they're the exact opposite? Well, it has to do with nuclear binding energy. So the binding energy per nucleon is greatest around iron 56. So you can see right here, that is the peak of this kind of shape right there. And what that means is if we have smaller nuclei and we fuse them together to make a larger nuclei, that's going to give off energy. It's also true if we had a larger nuclei, if we split it up into two smaller nuclei, we're going to be headed towards that iron 56 and it's going to give off more energy. Right? So where is that energy coming from? Well, a small amount of mass is converted to energy. You guys are probably familiar with the E equals mc squared equation. For example, let's take a look at the helium-4 nucleus. So the mass of individual nucleons, if we took a look, there are 2 protons and 2 neutrons in helium-4, and I have the mass of these separate ones. So if I go, hey, the mass of the helium nuclei should be 4.03188 AMU, but when I actually take a look at the mass of helium-4 nuclei, it's 4.00150. So you can see that this is actually smaller than what we would expect the mass to be if we just added all the parts together. How is that possible? The difference is 0.03. It's a small difference. I'll give you that much, but let's see what happens when we plug that small difference in mass into the E equals mc squared equation. So we get the mass, right now it's in grams, so I got to convert that to kilograms, and then I times it by the speed of light squared, right? So the units on that are meters per second, and then we square that whole thing, and we end up with a really big number. So the moral of the story is a small amount of mass is converted to a lot of energy. So let's talk about chain reactions. Fission is initiated by a slow-moving neutron. So we start here. You see I got the slow-moving neutron, and it hits this uranium atom, and it gets absorbed, which makes a uranium-236 from 235, and it's unstable. So basically, we had a relatively stable nuclei. We added a neutron to it. We made it unstable. So that nucleus absorbs the neutron, becomes unstable, and then it's going to split into two nuclei and also give off more neutrons. On average, 2.4, meaning sometimes it gives off 2, sometimes it'll give off 3. It's an average of 2.4. So now those neutrons, they're being ejected. They can go on to start another fission reaction. So that's how we're going to get a chain reaction. The neutrons being given off can go hit and collide with another uranium-235 nuclei. The uranium-235 can absorb it and become 236 and unstable, and again, another fission reaction. So this process can continue, and if it's unchecked, it can grow rapidly out of control. It'll release a bunch of energy, and it could result in like a violent explosion or a meltdown depending on where it's occurring, right? If you're trying to contain all that energy, you can get an explosion. If it's a power plant, it's going to be releasing too much heat. You're going to have a nuclear meltdown, right? Critical mass, another vocab term. The critical mass is the amount of fissionable material large enough to maintain a chain reaction of fission with a constant rate. So it's kind of a misnomer. Just because you have the critical mass, if you have the right amount of mass, it doesn't mean you're actually going to get the chain reaction. So it's kind of a misnomer because it's not just mass, right? If I had critical mass, but I flattened it out to look like a thin sheet, all right, well, I need a chain reaction. So when I give off a neutron, it needs a bump into another one. When it's flattened out, that neutron can go in any direction, and when it's flattened, it's less likely to bump into something. So the critical mass isn't just the amount, but it's also going to be the shape. So how do nuclear weapons work? Well, here is it's overly simplified schematic of the uranium bomb little boy. So you can see the uranium is in the yellow, and you can see it's been split up into two subcritical masses. So basically, if I were to combine these two together, then I would get the critical mass. But before we're carrying around a bomb, we don't want it to just go off. We have those masses separated, and when the bomb's dropped, they have pretty much just like a bullet. They shoot the two pieces of uranium together so that when they combine, they achieve critical mass, and you'll get a uncontrolled chain reaction. You contain all that heat and all that energy and all that pressure until it explodes. You end up with a nuclear explosion. And if they're so easy, I just saw a pretty simple schematic. I feel like that should be top secret classified. Why doesn't everybody have one if they're so relatively simple? Well, first, you need a nuclear reactor. So if you have a nation that has a nuclear reactor, they have the material needed to make a nuclear bomb. But the thing is, uranium-235 is fissionable, and it's the less abundant isotope of uranium. Most uranium is uranium-238, and when you give a neutron to uranium-238, it'll absorb it and it won't split. So it's not fissionable. It's not going to produce this chain reaction, whereas uranium-235 is. So you have to be able to purify uranium-235 from uranium-238. Like uranium ore is mostly 238, so you got to somehow separate uranium-235 from that, and it's very difficult. I would recommend watching this video, What Keeps Nuclear Weapons from Proliferating, the hardest step in making a nuclear bomb, by the engineer guy on YouTube. Moral of the story is, these two things are chemically identical. Almost all their physical properties are identical as well. The only difference is it's about a 1% difference in mass. So you got to separate them based on mass, and it's very difficult. So using nuclear power for non-destructive purposes, right? We can use nuclear fission as a power source. So power plants, they use the fission and they convert it into electricity, and we're going to take a look at how they actually do that. So things you need enriched uranium. You need to enrich it from 0.7% to about 3 to 5% of uranium-235. So you got to start there. And usually it's in the form of uranium oxide pellets or zirconium or stainless steel tubes. So you have these tubes and you fill them with uranium, and that's going to be your reactor. That's your fuel rod. You also need control rods, and what they do is they absorb the neutrons so that you can control the chain reaction. If this chain reaction went unchecked, you'd have a meltdown. It'd be giving off too much energy. You wouldn't be able to convert all that energy into electricity. It'd get hot. It would melt down. So you need control rods that are basically just going to absorb the neutrons and stop the chain reaction. You also need a moderator, because you need to slow down those neutrons. If they're moving too quickly from the other fission reaction where they're being given off, they won't get absorbed by the other nuclei. So you need a way to slow down the neutrons. So you need a moderator. Typically they use water or graphite. You need a primary coolant, which I matched the color here so you can see it's the light purple color. And it's pressurized coolant that cools the reactor core and it stays contained. So the stuff that is in contact with the radioactive material doesn't actually ever leave the reactor. It's part of it. It's a closed system. What we're going to do is we're going to heat up that coolant and we're going to transfer the heat to a secondary coolant. So that's where the secondary coolant comes in. It takes the heat away from the primary coolant and it makes steam, which can then be used to turn turbines, which produces electricity. And that's the moral of the story, right? So if we take a look, right here is where all the heat is being given off. It heats up this primary coolant. You move it to a steam generator where all the heat heats up the secondary coolant That steam turns a turbine, creates electricity, and then you have these condensers, because you still have, hot steam, so you need to condense it in order to circulate that water back. So you have these condensers, and that's where these cooling towers come in. If you guys are familiar, you've probably seen these and been like, what the heck are they? They cool the water so that it can get pumped back in, and the whole process is repeated. What about this nuclear waste I've heard so much about? So when you're using nuclear power, you're creating a lot of radioactive material. It needs to be stored for almost 300 years if the plutonium is reclaimed from the waste. So when you're using uranium, one of the byproducts is plutonium. The plutonium you can use for other different kinds of nuclear power plants. So if you reclaim the plutonium, you can store it for only 300 years. Only 300 years. Whereas if you don't reclaim the plutonium, the half-life of the plutonium-239 isotope is 24,000 years. And it's estimated that you need to give it at least 10 half-lives before the material can be considered safe. So you pretty much got to store these things forever and ever and ever, which is a real problem. So how do we store these materials? Well, there's a couple sites where they more or less just bury it in a mountain, which is problematic too, because what if anything leaks? It can get into the groundwater. You're talking about pretty much a permanent contamination. So it's problematic, to say the least. So let's talk about fusion. So upside to fusion is the energy that is given off during fusion reactions is significantly greater than fission reactions. So if we're talking about which one do we get more energy out of, definitely fusion. And it's an abundant fuel. You need hydrogen. It's the most abundant element in the universe. So we have fuel. And there's a lack of radioactive waste. The byproducts aren't radioactive. They're safe. But here's the downside. So first off, you need to make a bunch of energy in order to get a fission or a fusion reaction to go. These positive nuclei don't want to come together. Like charges repel. So you need a whole lot of energy and a whole lot of pressure to get these things to collide so that they can actually stick together. You need to overcome that repulsion. As of right now, the energy needed to start the reaction is about equal to the energy we're able to get out. So it's not a economic source of energy at the moment. It's always been, if we can figure out how to make this economical, this is the energy of the future. So how do they do this? What does this fusion reactor look like? So one of the most popular ones, the tokamak fusion chamber. So the way it works is, let's pretend this guy isn't here because he's going to have a bad time soon. The way the fusion chamber works is you create an area with a magnetic field. So we're going to use a positive magnetic field, and it's going to be positive kind of all around in this circle. And then what is that going to do for us? Well, if we injected some hydrogen nuclei, some H pluses in there, they're going to be contained into the center because they're surrounded by positive charges that are repelling them. So we pump in some hydrogen, we add a bunch of heat to it, we make sure it's only hydrogen in there, right? We create a vacuum, we add that hydrogen plus, and then we get them to fuse. We add a bunch of energy till they make helium. So we fuse those hydrogens together, they make helium, and what happens when that happens is it gives off a neutron. So a couple neutrons are ejected out of that fusion reaction. Well, neutrons are neutral, so they're not going to be affected by this positive electromagnetic kind of cage that it's in. So they'll be free, they have a lot of energy, and they'll fly off into the containment vessel. So the containment vessel will then absorb those neutrons and the energy from that neutron, and that's where they can convert that energy into electricity. All right, so as the neutrons are emitted, they're absorbed by the containment vessel. All that energy is converted into electricity, and that's how we can use fusion reactions to make electricity. This is what it looks like inside. Pretty cool. Definitely feels futuristic, so fingers crossed one day it becomes a thing. Destructive uses for fusion, though, we're talking about good things. There's always bad things, right? Science is a tool. You can use it for good or you can use it for not good. So if you ever heard of thermonuclear weapons, they're talking about fusion bombs. Not fission bombs, but fusion bombs. So the atom bomb, the atomic bomb, this is what they're talking about. So how can we create a bomb that's going to overcome these repulsive forces to make fusion happen? And this is, I think, pretty interesting. So you got to have a lot of energy just to get the fusion reaction to happen. So the way they do that is they have a fission bomb. So we have a fission bomb exploding, giving off a bunch of energy, which is then going to power the secondary fusion reaction. So basically, the fusion bomb is powered by a fission bomb. It's interesting, super destructive. So summarize. What can you say about nuclear fission and its applications, nuclear fusion and its applications, as well as how nuclear power plants work? All right, I hope you found that helpful. Okay, bye.